Alright, so in this video we're going to be covering the concept of bloom filters. And we're going to be doing that primarily in Python and with the help of some Pokemon. So, as Professor Oak says, welcome to the world of bloom filters. By the way, the content of this video is going to be very heavily based on a blog post on my blog, which I will just bring over here into this window. And the link for this blog post can be found in the description of this video. So feel free if you want more information on what we're covering in this video, that will be found on the post. So I will leave the link in the bottom. Anyway, so the main idea of a bloom filter, or the too long didn't read version of that, is bloom filters are really just a lightweight version of a hash table. So just like hash tables, they support very efficient lookups and insertions. I guess one pro compared to a hash table is that they're also very space efficient. So bloom filters are more space efficient than hash tables. However, the space efficiency comes at a cost of possibly having this false positive for entry lookup. So that basically means if you're consulting the bloom filter whether or not an entry is located in the data structure, you may occasionally get the data structure to tell you that an item is in the list when in fact it isn't. So that's a false positive. You will not ever get false negatives. That is, you will never get a bloom filter telling you that the item is not in the list if it actually is, but you do have this possibility of false positives. So a bloom filter is a probabilistic data structure, and this probability could be made to be quite small, but it depends on your purposes of whether or not this is something that you are okay for sacrificing for the improved space efficiency. So when would you like to use a bloom filter? So this is kind of a general answer to that question. So if you want a data structure that allows for very fast lookups and insertions, and you also care about the space that the data structure takes up, and I guess also along with that, you don't necessarily care whether or not the data structure sometimes indicates an item is present when in fact it's not actually in the data structure. So when might that be a case? When might you not care about that? So an example is that maybe you run a website, you want to keep track of some IP addresses that are blocked, and you don't necessarily care if the blocked IP addresses occasionally are able to get through and access the website, but you certainly don't want to prevent any unblocked IPs, potential customers say, from accessing your website. So this is an example of when a bloom filter might be nice, because storing an arbitrarily long list of IP addresses could be expensive depending on where you're hosting this at. So a bloom filter might be a nice alternative to using a hash table in this instance for this particular case. If you want more examples on when bloom filters might be a good data structure to use, the Wikipedia page has a number of examples and also real-world situations where bloom filters are used as a data structure. So I encourage you to consult that page as well. Okay, so now that we have kind of the basic idea of what a bloom filter is, when it can be used, etc., we're going to go over to this file over here, which is an empty Python file, and we're going to code up a toy example of a bloom filter that serves the purpose of being a Pokedex. So if you're not familiar, a Pokedex is a device that allows any Pokemon trainer to determine if they've seen or captured Pokemon. So as you might expect, this device needs to have fast insertion and lookup cost. So anytime you see a Pokemon, you want to be sure very quickly whether or not you've seen it, and if you capture the Pokemon, you want to very quickly put that data into your device. And in this case, for using a bloom filter, of course, we have to be okay with the fact that we might get false positives. So that means that if we're encountering a Pokemon, we have to be okay with these instances of the Pokedex telling us that we have seen it before, when in fact we have not. But fortunately, we will not get these instances of it being a false negative. So anyway, I don't know whether or not you'd actually use this for a Pokedex. You'd probably want to know for sure. And there's not that many Pokemon where this really is an issue for space. But again, this is a toy example, so kind of bear with me. Anyway, so bloom filter really consists of two main ingredients. So the first ingredient that it consists of is something called a bit vector. So you can probably ascertain what a bit vector is just based on the name. So a bit vector, in Python anyway, is really just a list of bits. So it's a list of components that can be either 0 or 1. And for the purposes of this example, I'm going to define this bit vector to be of size 20. So there's going to be 20 zeros in this bit vector. So if I print out bit vector, it's just giving me a list of 20 zeros. Very exciting. The other component of a Bloom filter is something called a non-cryptographic hash function. So that's kind of a mouthful if you've never heard that before. Really, all we care about is it's a function or a mapping that allows us to put something in, let's say Pokemon, and get something out of fixed length. Let's say in this case, a hash or a number. So that number is going to be used to correspond to entries in the bit vector. And we're going to use those entries, we're going to turn on certain bits in the bit vector to indicate that we've essentially captured a Pokemon. So let me show you what I mean. We're going to make use of, again, as I mentioned, these non-cryptographic hash functions. The non-cryptographic comes in because these are not used for cryptographic purposes. There are hash functions that are. Those are more computationally expensive to use and maintain. We don't necessarily care about the properties of cryptography for this application, so it doesn't make any sense for us to use a cryptographic hash function that's more computationally expensive when we can just use ones that don't care about cryptography. Oh, geez. Anyway, so there's a library called PyHash, which allows us to have access to a number of non-cryptographic hash functions. So if I say import PyHash, I can make use of these things. If it's still confusing, just think of these things as black boxes, which will essentially take in the Pokemon and will spit out some number that we'll use to indicate where to turn on bits in the bit vector. So the two non-cryptographic hash functions that we'll make use of have the names of murmur and f&v. So I'm just going to write that down. Non-cryptographic hash functions, murmur, and f&v. So these are very well-known, well-studied non-cryptographic hash functions. And again, PyHash kind of goes through the dirty work of actually implementing these things so we can just call them and invoke them. So I'm going to create two objects called f and v, which are going to be equal to PyHash that f and v 132 and also murmur, which is going to be equal to PyHash dot murmur 332. So these numbers are just kind of different flavors of the hash functions. You don't really need to care so much about these numbers here. These are just, again, different flavors of the murmur and f&v hash functions. If it's easier, just think of them as black boxes. Okay, so what we want to do is we want to, again, use our Bloom filter. We have the two ingredients now. We want to use the Bloom filter as a Pokedex. So let's go back to the slides. Let me go down here. We've encountered two Pokemon. We've encountered a Pikachu and a Charmander in the wild. I know that you probably are never going to encounter a Charmander in the wild, but just bear with me, it's an example. We've encountered them both. What we're going to do is we're going to store them in our Pokedex. So we're going to run Pikachu and Charmander through these hash functions. They're going to come out on the other side, don't worry. So Pikachu is going to run through the f&v hash function, and out of that is going to come the number 13. Likewise, we're going to run Charmander through the f&v hash function, get the outcome of 5. And likewise, we're going to do the same with murmur. So these outputs, again, you don't have to worry about how they're computed. It's just these are boxes that take some Pokemon, and on the other side, we have these numbers that will correspond to the indices in the bit vector. So let's actually write that out in the Python file here. So I'm going to say calculate the output of f&v and murmur hash functions for Pikachu and Charmander. So what we can do is let's call this f&v Pika, and this is going to be equal to f&v Pikachu. And what we're going to do is this is going to give us a number. This is going to give us quite a big number. And since the toy example that we're dealing with consists of a bit vector of only size 20, I'm going to mod whatever we get mod 20, so that way I get a number between 0 and 20. So that's what I'm going to do there. I'm going to do the same thing with Charmander as well. So again, we're taking Charmander, we're running it through this hash function. We'll call it murmur char, and we're going to feed this murmur and Charmander. So if I print out both of these things, f&v Pika and also f&v Charmander, then let's see what's the problem here. Probably the murmur Berber char. Okay, there we go. So I also need to do the same thing for, let's see, so I have two more things that I actually need to do here. So I need to do the FNV for both Pikachu and Charmander, and I need to do the Berber hash function for both Pikachu and Charmander as well. So let me just add those in quite quickly here. So hashing in Pikachu, I think all that looks good. Okay, so now if we print out the FNV of Pika char, and then also the Berber, the output of the Berber hash on Pika and char, then we'll get 13, 5, 10, and 9. These are exactly the same numbers that we have in the slide here, just because I've pre-computed the hashes for these Pokemon and I know what the outputs are. So once we do that, we get these numbers. What we're going to do with these numbers is we're going to turn on the bits at the relative locations, the respective locations of these hashes. So for instance, we have the numbers 13, 5, 10, and 9. I'm going to consult the bit vector and I'm going to say turn on the bits at location 13, 5, 10, and 9. And that's going to indicate to us that there's been, Pikachu and Charmander are now stored in our Bloom filter data structure. So let me actually do that to reflect this change. So I'm going to say bit vector of FNV Pika is equal to 1. I'm going to do the same thing with the Berber function as well. And of course we need to do the same thing for Charmander. So FNV char is equal to 1. Berber char is equal to 1. And if I print out the bit vector, let me just print that out, we see that the bit vector now has 1s at the locations corresponding to the hashes that we obtained from hashing Pikachu and Charmander using both FNV and Berber. So let me go back to the slides, and just in case that wasn't clear, we had this empty bit vector, which was just in this case, a bit vector of all zeros. We captured Pikachu and Charmander, and then we have reflected that by updating the indices of this bit vector with 1s. So let's continue. We keep walking in the tall grass and we happen upon a Bulbasaur. So Bulbasaur appears and we want to consult our Pokedex to determine if we've encountered this Pokemon before. So what we're going to do is we're going to do the same process. We're going to take Bulbasaur and run him through FNV and Berber. And the outcome of doing that is going to give us two numbers respectively, 11 and 8. And what we're going to do is we're going to check whether or not the indices of those two numbers that we got have been turned on. If either one of those locations in the bit vector are 1, or let's just say if both of them are 0 or one of them is 0, we know that Bulbasaur has not been caught, and we can capture him and we can add him to the Pokedex. If both of the entries 11 and 8 are 1, however, we can't say definitively that Bulbasaur is in the data structure. Remember, this is a probabilistic data structure, so we do get these false positives. So it's possible that a Pokemon comes along. In fact, it's very probable, since we have a bit vector of size 20 and there's, let's say, 151 Pokemon in this universe, that it's very possible that we're going to get some collisions and we're going to get some Pokemon hashed into the same value. So as we capture more Pokemon, this bit vector of size 20 is going to be quite bad. It's going to not allow us to determine with any certainty whether or not a Pokemon we've encountered has been captured. In this case, again, it's a toy example. We've captured 2, we're capturing a third. It works okay. So let me actually go back to the code and show you what I mean. So now we're going to have the same process. A wild Bulbasaur appears. And what we do for that is, again, we run him through both of these hash functions. So FNV and Berber. We just make a few changes here. So we'll call this FNV bulb, Berber bulb, and again we want to run the string Bulbasaur through these functions. So if we do that, if we print out FNV bulb and also FNV char, actually I'm sorry, Berber bulb, that's what I need. So if we print this out, we get 11 and 8, which is, again, I've done the hashes before, so I know what the values correspond to. So those are the hashes that we get from running Bulbasaur through our Pokedex. Going back to this, what we do now is we check, okay, let's say, is bit vector of FNV bulb, what is the value of this thing? and what is the value of the F and V, or rather murmur of bulb. So the value at both of these locations is 0. Again, if we had a value of 1 and 0 or 0 and 1, we could ascertain that this particular Pokemon is not in our blue filter or our Pokedex, so we could go ahead and capture it. We won't have any duplicates. Again, if we have both 1s here, it could be that Bulbasaur is already captured, that he's already in the Pokedex, but it's a maybe. It's a possibility of getting false positives. So again, this is kind of a short little toy example. Again, if you do have more questions, hopefully those will be answered on my blog post, which goes into a little bit more detail about how this works and also some of the problems. This section goes over what happens if you have collisions, and also some equations that just go over what's the optimal number of inputs and hash functions that you need. So it goes over that in a little bit more detail. If you are interested, please do check it out. That's all I'm going to do for this video. If you have more questions, comments, or whatever on bloom filters or anything else, please let me know. Thanks again for watching, and have a great day.